Hello everyone, my name is Jonathan Parlett, and this is going to be the second in a series of videos to help you out with some C fundamentals coming into CST 60. Today we're going to mainly discuss memory and pointers, and we're going to discuss things in this order. So first, we're going to show a simplified model of memory as a table. Then we're going to discuss pointers and the operations performed on them, to include the address of operator and the dereference operator. And then we want to talk about pointer addition. But before we do that, we need to cover some other topics that are related to it, topics that use it. So we're going to talk about arrays and pointer addition. Then we're going to talk about the type system in C and the sizes of different types. Then we're going to discuss just pointer addition on its own and what it does. Then we're going to move on to memory management, where we're going to discuss malloc, which is how we request memory from the operating system, and free, which is how we return memory to the operating system. So let's start with how we're going to visually represent memory as a table. So we can think of the memory allocated to a program as a collection of cells that hold data items. Data items such as the integer I equals 55 or the character C equals A. And you can see here we have a bunch of cells in a table. You can see some of these cells have the values of the variables that we specified. So I corresponds to the cell with the 55 in it, things like that. And then you have some other cells that are just zeros. So these memory locations occur in some physical order. So there's the lowest location and the highest location. We're going to label them in this order from the lowest, taking 0 to be the lowest and n to be the highest, and just being a variable amount of memory, really. So you can see we've added a second column, address, which is really just the index of a given element in our table. So A, for example, has the index 1 in our table. So finally, we need to add the stack and the heap. So like we discussed previously, the stack starts at the highest address and the heap starts at the lowest. So we add the stack to the top of our table and the heap to the lower part of our table. I should specify that we're talking about the section of memory that is allocated to a specific program, not the entirety of the memory in your computer, which is why we have the stack and the heap. We're discussing the stack and the heap for a specific program that we are running. We're going to take n to be 64, so we can deal with just 64 cells of memory, just a small amount, so it's going to be convenient to work with. So to illustrate these next points, let's first grab this table and take it over to our whiteboard. Let's make sure we can draw on that. Okay. So we're going to say that a row in our table can contain a single variable of any type. So it can contain a single integer, a character, an unsigned long, etc. And what this means is that one of these cells can correspond to a declaration such as int I equals 55 again. So this corresponds to this, which means this is stored at location 3 and its value is 55. And like so, we could have this declaration in code, the character C is equal to A. And this would correspond to this data item and this location. Cell 1, data A. This is what I mean when it's stored a single variable of any type. So those of you who are more familiar with C and memory will notice that this means we're ignoring the size of the type in our table model of memory. By saying we can store a single data item in each cell, we're saying we're ignoring the size of the type of that variable. If you don't understand this point, don't worry about it. We're going to discuss this in more detail later. So we're sometimes going to omit labels such as the stack and heap, just so we can save space on the slide. So if we're just discussing, say, like a static declaration or something, then the heap is kind of inconsequential, so we might just remove it just to save space. But this is a fairly precise model of memory in a table. So each variable or data item is stored in memory location. That location has an address, which is another column of our table. And it's really just an index in the table. So in the same way, when you're looking at an array, each element has an index. This is just really a table. it has each cell has an index, and that's the address in the table. So you should also note that you'll never work with memory addresses this small. Most of the addresses you'll work with in actual computers will be in the millions, and they're going to be best represented with hexadecimal notation because they're just very large and cumbersome to work with. But let's move on to pointers. So first, let's discuss the basic concept of a pointer. So the basic idea of a pointer is something that tells you where something else is. So you can consider Bob, and Bob will point to McDonald's. So let's draw Bob. Little stick figure. He is pointing somewhere, and where he is pointing is McDonald's. So if you know where Bob is, you can look where he's pointing to find McDonald's. So you're like, oh, I can see Bob. Well, then I know where McDonald's is. I can see McDonald's. So it would be reasonable to call Bob a pointer to McDonald's. So moving on to pointers in C. Let's refresh our whiteboard real quick. So a pointer in C tells us where a variable or data item is located. So if we have the integer I equals 49, we'll say that I is stored at location 63, which is why we specified that the data at location 63 is 49. It's the value of the variable. So to locate I, we just need its address, 63. So this is what a pointer in C is. It's just another variable that holds an address. It holds the index of something else in our table. Since an address is just a number, a pointer is just a number. A pointer to I would have the value 63. So now let's take this whole declaration over to our whiteboard so we can talk about it a bit more. And let's make sure. Okay. So we have the integer I equal 49. Again, that's still stored at location 63. Now we have the int pointer j. It has the value 63. It is a pointer to I, and it's located at the address 62. So j is Bob and I is McDonald's. Since pointers are variables, they're stored somewhere in the table. When we declare them, they're statically allocated integers. So they're stored on the stack. You can see these are stored right next to each other. They are both on the stack. So j is stored at location 62. It is a pointer to I. So its value is the address of I, namely 63. So let's go over this more explicitly. So j is stored at location 62. I is stored at location 63. The value of j is the address of I. So the value at location 62 is the address or index of I in our table. Okay, that is what a pointer is. It holds the address of another data item or variable, etc. So moving to pointer operations, let's start with the address of operator. The address of operator, the ampersand, is applicable to any type in C, not just pointers. It returns the memory address of the data item you use it on. So we can consider it in this context, the same example we used before. I'm just illustrating with the print statements, but let's illustrate this with our table. So in the context of our table, the address of I is its index in our table. So the address of I corresponds to the location of I, 63. So this would be equivalent to 63 if you were comparing it in C. And similarly, like this is not restricted to pointers or it operates on anything, right? So what is the address of J? Well, it's going to be equivalent to 62, the address of that pointer. Okay, because again, J is another variable that we statically declared just in our code right here. So it's also stored on the stack. So a pointer is just a memory address. The ampersand operator returns a memory address. It returns a number. It returns the location, the index in our table, etc. So in effect, it returns a pointer to the item you use it on. So this is why it makes sense to do something like int pointer j equals address of I. We are printing the, we are assigning the value of j, the address or the location of I. So this is a more practical way to get a pointer to a statically declared variable. Continuing with the pointer operations, let's talk about dereference. So when you dereference a pointer, you're accessing the value at the location specified by the pointer. So again, with our previous example, let's go over this in our table. And let's clear up some of this because we're done talking about address of. So let's just get rid of that. Okay. So we already know what address of does. When we dereference j with our star operator, we are referencing the value of I. This corresponds to 49. This would be equivalent to 49. And again, look at the chain here. So first you have that j has the address of I as its value. When you are dereferencing j, you are looking at the value at the location specified by j. So we would call this the value at j, which is the value of I. And when you are using the star operator, you are referencing that variable completely, right? Like you can assign to this, you can mutate it, you can do whatever you want. So if we set this equal to 3, then this is no longer 49. This becomes the value 3 at this memory location right here. Okay. So before we move on to pointers, let's illustrate this with an example. So let's take the integer I, we're going to set it equal to 49, just like we did. We're going to have the int pointer j, and we're going to set it equal to the address of I. And now let's print a few things. We're going to print addresses using hexadecimalization. Don't worry about the value if you're not familiar with hex, just worry about the relative value. Look at how they're the same. Okay, so first let's print the address of I. We're going to print that in hexadecimal because it's going to be a very large memory address. And we're going to use ampersand I. Okay. And then let's print the value of j, which we'll just get with j. Okay. So now let's run this code. So you can see that the address of I is the same as the value of j, which should be pretty obvious because that's what you assigned it to be. But still, let's make sure. Okay. Now we're going to print the value at j. And this is going to be an integer. So we're going to get that with star j. And we're going to print the value of I. And that we just get by passing in I, which will also be an integer. So again, you can see that you get the same thing. So the value at j is the value of I, namely 49. So let's print this value again, but let's prove we can assign things, right? So star j equals 6. And we can see that we have modified the value at j, and we have modified the value of I. Okay. There is nothing odd going on here. You are referencing I completely when you dereference j. If you modify the value at j, you are modifying the value of I. Okay. So now let's move on. We want to discuss pointer addition, but again, like I talked about before, we have to discuss some other topics. So first, we're going to cover arrays. So arrays are closely related to pointer addition. So we're going to explore them first. So arrays are one of the simplest data structures. They are just a collection of contiguous memory locations that contain items of the same type. So consider this statically allocated array A equal to 4, 5, 6. So the simplest way you would draw this would just be a box split into 3 cells. 4, 5, 6. okay, with the index 0, 1, 2. So that would be represented in memory like this. And let's actually grab this. And let's see how these relate to one another. Okay. So this. So this corresponds to 61. Obviously, its value is 4. Corresponds to location 62, 63, so on and so forth. Okay. So the variable a, right, is called the base pointer of the array, and its value is the address of the first element. In this case, 61. So coming back up here, let's discuss a. So if we dereference a, right, a, let's start this a little separately. So a corresponds to location 61, right? It's equivalent to 61. So star a corresponds to the value at 61 for the first element. And you're probably already familiar with array indexing notation. So a sub 0, obviously that's the first element of the array. So it is also the value 4 specified or held at location 61. So it is a plus 1. So a plus 1 will correspond in our model of memory anyways to location 62. And if we are dereferencing a plus 1, then we're referencing the second element, 5. And this is obviously also equivalent to a sub 1. 5. So in particular, we can state this as a plus I, or value at a plus I, is equivalent to a sub I. Array indexing is kind of just shorthand for this. Array indexing is shorthand for pointer addition plus dereference. Okay, and that's all I'm saying here. So let's go over this more carefully with the code example. And just paste this in, erase what I had previously, and let's format this a bit better. Indent these. Okay, so first we have our static declaration of our array, a sub 3, with 3 elements. We're first going to print the value of a. Remember, a is a pointer, so we're printing a memory address here. It is the base pointer. After this, we're going to go through our the elements in our list, and we're going to first print the value using pointer addition plus dereference, and then we're going to print the value using array indexing. And then we're also going to print the value of a plus I. So not dereferencing it, just printing the value of that computation. Okay, so let's go ahead and run this. Oh. And let's add a new line here so we can get some not yucky output. So first, the value of the base pointer is just some address, very large, blah, 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 yucky. Okay, you can see that this is indeed equivalent in C. A plus 0 value at equals 4, same as a sub 0 is equal to 4, and this is the same for all indices I. Now you can see the address of these locations is not increasing in increments of 1. So if you are familiar with hexadecimal, you know C is the same as 12. So the next element should be D, or the next address would be D, if we were going by our description of things. But like I said, our description of this table is simplified. It's a simplified model. Okay, in particular, it doesn't capture this exact thing. This is a difference of 4. You can see it first goes from 0 to 0, or from C to 0, and then to 4. So it increments in 4s. not in ones like we would expect. So we're going to explore why this is true, and we're going to learn a few more things about C as we do. Okay. So to understand this, we're going to need to understand a little bit about the type system and the sizes of different types. So the atomic unit in memory in C is a byte. What I mean by when I say that is just, it's the smallest unit of memory that we'll ever care to address. It's how we're going to discuss memory at the most fundamental level. A byte is just 8 bits. So each type in C, when we're talking about types, we're talking about the integer data type, the character data type, the unsigned integer data type, whichever. So each type in C takes up a certain amount of bytes of memory. Each of the cells in our current table actually corresponds to a certain amount of bytes based on the type that is stored there. So to discuss sizes a bit more, let's look at some sizes in C. And to do that, we're going to need the function size of. So the size of function, which is defined in C, takes either a type or a variable as an argument. A type being just the word integer, the string int, whichever. And then a variable obviously being a variable. So given a type, size of returns the size of the type in bytes. Given a variable, it returns the size of the type of the variable in bytes. Generally, there are some weird cases where it does not do that. What it does not do, it does not return the length of an array. It does not return the length of any finite data structure. Okay, there is no way to do that in C. This is specifically size of is related to the size of a type in C, nothing else. It is not like the len operator in Python. Okay, so now let's look at the size of some types in code. So be aware that sizes may be different on different hardware platforms, different computers. So these may not be the same on your system, but most likely they will. The areas where you see different sizes of data items is in like embedded computing or very specialized hardware. But anyways, let's check the size of types using some code below. So we're going to check the size of an int, the size of a car, and the size of 2 different types of pointers. And don't worry about reading this slide too much because I'm going to run through it more slowly in my IDE. And let's just format this a little bit nicer. And let's comment out these, because obviously these are not actual code. Okay, so first we're going to print the size of integer, and then the size of character, and then the size of an int pointer and a car pointer. Okay, so the size of an int is 4 bytes. The size of a car is 1 byte. The size of any pointer is 8 bytes, no matter the type it points to. You can see it's the same for int pointer, int car. If I did like say car pointer, don't worry about what this actually is, but even that does not change like the size of the thing. It's still just 8 bytes. We're not really going to discuss why that is exactly, but understand that that's the case. Okay, so the size of an int is 4 bytes. You can remember that in the array example we were going over, the pointer was incrementing by 4s. Okay. So let's look more closely at adding to a pointer with the code example. Let's explore exactly what's happening here. So again, let me erase all of this. And let's paste this in, format this a little bit better. And let's full screen representation again. Okay, so first we're declaring 2 variables. One is going to be an int pointer, the other is going to be an integer. First, we're printing their value. We would expect them to be 0 because that's what we initialized them to. We said int pointer I equals 0 and int j equals 0. Then we're going to increment them. So we're going to add 2 to the integer pointer, and we're going to add 2 times the size of an integer to the integer j. Remember that the size of an int is 4, so you're adding 2 times 4, so you're adding 8. You might expect, if you were going by our model of memory, that I would be 2 after this. but that's not how it actually works. So these are actually equivalent. This is because pointer addition in C is defined as when you're adding something to a pointer, what you are adding is that thing times the size of the type that the integer points to. Okay, now let's look at more formal definition of this. So to be perfectly clear, if a pointer I is equivalent to a number J, then adding to I is equivalent to adding the same thing to J times the size of the type that I points to. Okay, so I have an int pointer I, and we have an integer J. The value of J is just some natural number. Think of it as like 4 or 2 or 3 or whatever, it doesn't really matter. The value of I is going to be the integer value of J, okay? If we're saying I plus 1, that will be equivalent to J plus 1 times the size of it. And more generally, if we're adding X to I, this will be equivalent to adding J plus X times the size of the int data type, okay? You can generalize this for any data type. Just replace int with whichever type you care about. So this is why the array pointer A is increased in increments of 4, since the size of the int data type is 4. So now that we're no longer ignoring the size of types, let's take our original table representing the array 346, and let's redraw it accurately. So each row in this table, 64, 63, 62, so these are integers. So each row actually corresponds to 4 bytes, 4 memory locations for each number in the array. So we need a total of 12 cells to represent our 3 numbers. Now let's reset my whiteboard real quick. And let's go take a look at our drawing of this, okay? And let's take this over to our whiteboard and just talk about it. Okay. So first we have to say that the value of A corresponds to this very first location that is relevant to the array, right? So A corresponds to this location, 52. A star actually corresponds to these 3 total locations or 4 total locations. Okay, corresponds to the value 4 that you get by looking at these 4 bytes. But obviously C just does this for you. Okay, A plus 1 is in fact not 1, or not like 1 more. It's not 53. It's actually 56. But obviously the value of A plus 1, or the value at A plus 1, is the value contained in these 4 bytes, 55 or 5. Let's redraw our original array to make this clear. Okay. So let's just draw 4, 5, 6. So each one of these corresponds to the 4 bytes here. And its value is here. And when you are adding 1, in fact, you are adding 4. So A plus 2, rather just A plus 2, corresponds to location 60, and the value at A plus 2 corresponds to the value in the 3rd location, which also corresponds to A sub 2. Okay, so this is really the most complicated part of pointers, is how pointer addition works and why it works and what arrays are and what's really happening. If you can conceptualize this part, then everything else is pretty easy. But that about wraps us up for pointers. This is just going over what we discussed. The table is almost still the same. A is still equal to that first location, 52. But you're actually referencing the four bytes starting at that location. So bytes 52 to 55. And when you're adding 1, you're adding 4. So instead of A plus 1 being 53, it's actually 56. Yeah. So now we're going to move on to memory management in C. Specifically, again, we're going to talk about how we request memory from the operating system with malloc. And we're going to talk about how we specify that memory is no longer needed, how we deallocate it or return it to the operating system, which we're going to do with free. So first, beginning with malloc, let's review its summary from the Linux manual pages. So they say the malloc function allocates size bytes and returns a pointer to the allocated memory. Because again, that's the argument specified by malloc. It takes an argument size of type size t, which is just an integer. Relating it back to our memory table, the malloc function accepts a number of bytes as an argument and returns a memory address, index of our table, to memory on the heap. So if we consider this table below, we're going to start from the bottom because we're referencing the heap now. Notice we've omitted the stack label. A call to malloc will return a heap address. We can use it to request memory for an int pointer like so. So remember what size of int is. It's 4. So here we're actually requesting 4 bytes on the heap. So it's going to return the address of the start of a 4-byte sequence that we will say we now own. Okay. So in this instance, malloc may return address 0. 0 to 3 would be used to store an integer. Let's just take this over to our whiteboard. Okay. So if this, return value corresponds to 0, so it equals 0. So now if we were to do, say, star I equals 6, then this was initially junk values in all of these bytes, but this now all corresponds to a single value whenever we're referencing it anyways. It's the value 6, which in binary would actually be, so we'd have like some 32 bytes of preamble or a bunch, and the value of 6 is just 4 and 2, so 1, 1, 0. So we'd have a bunch of preamble. The total length here is going to be 32 bits equals 4 bytes. Yeah, and it's the value 6. Okay. So notice the use of the size of. So this means we're absolutely going to request the correct amount of storage for this type we're pointing to. The size of these types, again, may vary from hardware to hardware. So using size of keeps our code as hardware independent as possible. And it prevents you from making dumb mistakes. Like you wouldn't want to remember the size of an integer, and then maybe one day you just think it's 5 for some reason, and you end up allocating more memory than you meant to, or less, which would be even worse. So let's go over how we can create our own arrays with malloc using a code example. So let's take this into our IDE and go over it more slowly. So first, we have our int pointer, A. We are allocating 4 times the size of an int, right? So what does this mean? So size of int, 4 bytes, is enough space for 1 integer. We want enough space for 4 integers. So we just multiply it by however many elements we want. We want to store 4 integers, so we need 4 times the amount of memory it takes to store a single integer. That's all this is doing. So this, in fact, is the same as, like, this is basically equivalent to int a sub 4. We have enough space for 4 bytes, or 4 integers. So we want to store, say, the first 4 multiples of 5. So that's what we're doing here. I is the index into our array. So from 0 to 4, a sub I equals 5 times I. and then we can print the elements. And this is really just to prove that, yeah, it works, right? A sub 0 equals 0, a sub 1, 5, a sub 2, 10, a sub 3, 15. And if we went further and further, we would have a sub I equals 5 times I. Okay, so how would this be represented in memory? We're going to make it more compact by saying that the addresses we're going to show is every 4th byte. So you can effectively look at this as just the collapsing of our table. So this is kind of convenient to have these two together, because in fact, one of these would correspond to 4 locations, right? Corresponds to locations 0 to 4. Here the value is 0, but obviously the value in these 4 bytes would correspond to 0 in this case, because that's the value we chose to store. But anyways, so now let's go over free. So again, we're going to talk a little bit more about dynamic memory. So this allows us to allocate memory programmatically. Say we want to allocate memory with malloc for a new game session every time a user connects to a server, for example. Obviously, we could have a lot of people connecting to our server. Say you have like 100,000 people connecting to like a World of Warcraft server or something. Eventually, we're going to run out of memory on the physical server. But eventually, some users will stop playing and disconnect from our server. So now we should be able to allow someone else to play, right? If you've ever experienced queues in a video game, it's kind of like that. We can do this by reusing the memory allocated for the disconnected player for a new session. So first, we would free that old memory. This is what we'd use free for. Free is the other half of memory management. Whatever memory you request from the operating system with malloc, you have to eventually return it with free. If you fail to free memory you allocate, it's called a memory leak. Memory leaks are sources of some mysterious bugs because they can occur at seemingly random to the programmer times. So considering the example of the GitLab game server, if it never reclaims memory, it would eventually not allow anyone to play. This is because eventually it would fill up, but it would never, eventually everyone would stop playing, right? Like as people stop playing, you can't add any new players. So eventually it would just become a dead server. You would have 100 offline players. And maybe eventually when those players signed in, they could reclaim their spot, but you would only have those players on your server ever for all time. So yeah. So let's go over one more programming example, allocating memory for a struct pointer and using free appropriately. This one is going to be kind of big. I think I'm just going to type this out myself so we can go over it as we write. So first, let's have our typedef struct data. Hopefully you're familiar with this idiom of typedef struct. It allows us to be able to write data like I, for example, instead of like struct data I. You're going to see this a lot in C programs. People really just don't like to write the struct tag. You could keep it and write struct every time, but people don't want to. Some people hate that people do this, but it doesn't matter. So anyways, we want a float pointer. We're going to store some data points, right? We're going to pretend this is like a data set from one of your lab sessions or something. So we're going to have a float pointer. We'll just call it like capital T. And a int L. This is going to be like length, or just we'll call it len. Yeah, so we want a pointer or an instantiation of one of these structs. Okay, so we're going to allocate, or we're going to create a pointer to it. So you declare that the same way you would for any other data type. So like data pointer D, and we're going to allocate memory for it. So we're going to say malloc size of, the same way you would for any other type. You can use this for the types that you specify. So size of data. It's going to make sure we have enough space for a float and an integer. Okay, So now the D, remember, which is the data, or maybe we'll call this values, because it's going to get very confusing. Just D, blah. And we need to allocate space for that, because that is also a pointer. So malloc size of float, because that's the type we're pointing to, times D sub len. Of course, we haven't said what len is. So let's initialize that. But len is not a pointer. It's just a static variable. So it already has had its memory allocated by the compiler because it is not in itself declared as a pointer. So we're just going to set its value equal to, say, 5. We want 5 data points. Okay. And this should have been vals equals malloc. Okay. So now let's iterate over our values and put some data in there, which is just going to be a bunch of floats. So we're going to have int I less than d len. Obviously, want to initialize I to 0, and while less than d len. Oh, we already did that. I plus plus. And we're going to say d sub vals equals I times 0.25 or something, just so we have some floating point values. So we're going to use the same loop to just print these values. So we're going to say printf vals sub I. It's going to be a float terminated by a new line, just like that. And let's make sure that all works. Okay, so you can see at each I location, and let's actually pass that in as well. So %d, and we're just going to pass in I here, so we can see our indices. So you can see at each ith location we have some floating point number. In this case, it's just incrementing in terms of 0.25. So we've requested this memory. We need to return it. Otherwise, this is memory leak. So you might be tempted to just do this free D, but free is not an intelligent, or it's not a smart function. It's not naturally recursive. It's not going to know that there's a pointer allocated here to vals and deallocate that as well. So in fact, if you just free D, you've created a memory leak. You never free the other pointer that you allocated memory for. The correct thing to do would be to first free D sub vals. Okay, just like that. Okay, so that's just the usage of malloc and free. We're going to use them a lot more in the next video. But anyways, to recap, hopefully you've gained a solid understanding of pointers and the basics of memory management. Next, we're going to put everything we've learned into practice by implementing a dynamic data structure in C. To end this off, hopefully this was a very complete definition of what a pointer is. By just sticking to the abstractions of what a pointer is, this Bob points to McDonald's, I think people miss a lot. It's what makes pointers hard to understand. If you don't understand everything in this definition, that's fine as long as you understand just the gist of it and you understand that there is a concrete definition. There is a concrete thing beneath that basic concept and idea. But yeah, hopefully a lot of this will be clearer when we go over a programming example next. But thank you for your time and thank you for watching.